Problem number 1 on the Sequences and Series study guide. We want to find the infinite sum here. We have a geometric sequence written in summation notation as an infinite series. Now first off, you have to recognize that this is actually a geometric sequence. The tip-off is the exponents, although it doesn't really look quite like a geometric sequence that we're normally used to, because normally we see our geometric sequences or series in the form of some first term a times a constant ratio r raised to the power of n or n minus 1, depending on how you write it. And this doesn't really look like that at first glance, but if you break it down and remember the rules of exponents, you can find out that it is actually the same thing. So remember that if you have something like, say, x to the third times x to the second, well, we all know that you can write this as x to the fifth. Another way to think of that is x to the 2 plus 3, or 3 plus 2, in the order that it is there. But the point is that exponent 2 to the n plus 2 we can rewrite as 2 squared times 2 to the n, essentially taking this and going backwards to that form. So that's going to be our first step. We're going to rewrite this series in a more familiar form. We're going to write it so it actually does indeed look like a geometric series that we're used to. So to rewrite that, I'm going to rewrite my sigma, my starting term n equals 0, denote that I'm going to infinity, and I'm going to pull that 2 squared out like I did before. And I'm just going to go ahead and write that as a 4, which is going to be my first term. So the next step we're at is we have this 2 to the n over 5 to the n. And again, it doesn't quite look like what we're used to, because normally we'd like to see just some fraction raised to an exponent like that. But again, remember how you handle exponents. If you have a fraction, and the entire fraction is being raised to an exponent, you can essentially distribute that exponent. So this would be like 1 to the n over 4 to the n, just like that. And I mean, think about it. Imagine if you have 2/3 squared, something like that. Well, think about what that squared really means. That's saying take the fraction 2/3 and multiply it by itself, the fraction 2/3. And when you're going to multiply fractions like that, you multiply across the numerators and you multiply across the denominators. 2 times 2 is 2 squared, 3 times 3 is 3 squared. And you can see the point I'm trying to make there, all heading us towards the fact that we can write this sum again as our first term 4 times that fraction 2/5 raised to the power of n. And now it almost looks like what we're used to now, except we generally see our geometric sequence general term formula written in terms of n minus 1. Also, we normally see it with starting term of n equals 1 and not n equals 0. But we've seen this before. We know we can just rewrite this as the summation from n equals 1 to infinity of 4 times 2/5 to the power of n minus 1. If you don't believe me, check it for yourself. Prove that those two are actually equivalent. That is a good exercise for you to do. Prove it to yourself. But the whole point is now this looks like something we're used to, and maybe now we can go about solving it like we know we should. So at this point, it's just a matter of remembering that we have a formula for the infinite sum of a geometric series, and that formula is we take our first term a, or if you want to write it a sub 1, that's fine too, divided by 1 minus r. So let's substitute our values in. Our first term is 4, our constant ratio is 2/5, and now it's just a matter of simplifying this and figuring out what we actually have. So 1 minus 2/5 is 3/5. 4 divided by 3/5 is the same as 4 times 5/3, so we're going to get 20 over 3 for our final answer for the infinite sum of this geometric series.